Welcome to the SAR channel, where sound and audio are demystified. The analog television system known as NTSC, National Television Standards Committee, was introduced in 1939. It was first made for screens only 5 to 10 inches wide, yet it stayed in use for more than 60 years, color was added in 1954, and stereo sound in 1984. But today, except for a few low-power or special stations, analog broadcasting in the United States has ended. High-power NTSC broadcasts stopped in June 2009 and were replaced by the ATSC, Advanced Television Systems Committee, digital standard. With ATSC, digital television, DTV, delivers better picture quality, surround sound, and widescreen images. It also helps bring television and computer technologies closer together. Since 1939, TV program delivery has changed as well. Now, over-the-air stations are just one part of a digital world that also includes cable, satellite, and the internet. The move toward digital TV began in 1986 when the FCC said it might give unused broadcast frequencies to mobile phone companies. TV broadcasters argued they needed that space for future high-definition signals, and in 1987 they showed Congress early analog HD receivers. They were granted the spectrum, but were also required to help create the new technology. At first, most people assumed analog HDTV was the best option. But in 1990, General Instrument introduced a digital TV system, which pushed the industry toward a digital standard instead. By 1992, 4 digital and 2 analog systems were competing. In 1993, an FCC advisory group decided a digital system should be chosen, but none of the proposals clearly stood out. The FCC then asked the companies to unite in a grand alliance and combine the strongest parts of the 4 digital systems into one HDTV standard. In 1995, the Advanced Television Systems Committee, ATSC, recommended the DTV format, and in 1996 the FCC approved it and required it for over-the-air broadcasting channel, and service rules came in 1997, and nationwide ATSC broadcasts began in 2009. Engineers faced a major bandwidth challenge when creating the DTV system. To handle it, ATSC designers chose 2 common compression methods, MPEG-2 for video and Dolby Digital for audio. Starting in July 2008, ATSC also added support for the H.264 MPEG-4 AVC video codec. ATSC video formats can use Dolby Digital audio, which can be decoded by the same home theater receivers many people already have, although not all DTV shows are broadcast in surround sound. Like video compression, Dolby Digital reduces audio bit rates by analyzing which sounds people cannot hear and removing or masking them. It uses psychoacoustics, the study of how the human ear perceives sound, to decide what can be safely discarded. Both lossy and lossless coding can be used on audio to lower the bitrate needed for storage or transmission. The same idea applies to video. Because video requires very high bandwidth, data reduction is necessary in almost all cases. Although video uses different technical methods, the goal is still to cut the bit rate. In fact, video can often be reduced much more than audio before you start to notice problems. The MPEG video compression standards are good examples of how these methods work. In normal daylight, the retina collects visual information at about 800 megabits per second. But the nerve pathways sending signals to the brain cut this down by about a factor of 100, because the brain doesn't need all the incoming detail. Video compression algorithms use the limits of human vision to reduce data through spatial and temporal coding. Research shows that our eyes notice changes in brightness more than changes in color, and that our sensitivity to both brightness and color is not linear. Audio engineers are used to thinking about frequency as cycles of a waveform over time. In video, spatial frequency describes how fast visual details change across an image without involving time. How a picture changes over time is called temporal frequency. Picture contrast can be broken into horizontal and vertical spatial frequencies. Since the eye acts like a low-pass filter, very fine, high-frequency details can be reduced through quantization without noticeably hurting image quality. The human eye can sense about 1,000 shades of gray, which takes 10 bits to represent, though 8 bits usually works well. Brightness, luminance, is detected by one type of receptor, while color, chrominance, uses 3. Because the eye is less sensitive to fine color detail, chrominance can be encoded with fewer bits. Video reduction takes advantage of similarities between pixels that are near each other in space or time. Highly random images with lots of entropy are harder to compress, but most images include predictable patterns. Video coding uses redundancy within a single frame and across multiple frames. Compression also uses what we know about human vision, called perceptual coding, to remove details we won't notice. Still images are transformed into spatial frequencies, so unimportant detail can be removed and the rest quantized. Temporal coding keeps keyframes and then records only the differences between other frames and those keyframes. Video codecs use these properties to reduce data while keeping important visual information. Raw digital video requires huge amounts of data. An analog NTSC video signal has a bandwidth of 4.2 MHz. According to the Nyquist theorem, digitizing it requires a sampling rate of twice that, or 8.4 MHz. At 8 bits per sample, that equals 67.2 megabits per second. Because a color signal includes red, green, and blue channels, the rate triples to 201.6 megabits per second. A 650 megabyte CD could store only about 26 seconds of this uncompressed video. Data needs can be reduced by lowering the frame rate, shrinking the image to a smaller size, or using fewer bits to code colors. More advanced methods look for unnecessary information within frames and across sequences, and then apply compression to the repeated data. These approaches can keep image quality high while greatly lowering bitrate. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. MPEG 1 and MPEG 2 video compression work in much the same way, so they can be explained together. Both rely on a mix of lossy and lossless methods to lower bit rates and can operate at many different bit rates and picture resolutions. Like the audio standards, the MPEG video standard describes only the structure of the bit stream and how it must be decoded. It does not lock in one specific encoding method, allowing the encoder to be improved or adjusted for different visual needs. Besides algorithm-based compression, MPEG uses heavy preprocessing to lower pixel counts, reduce how many frames need coding, change how signals are represented, and refine other picture parameters. MPEG 1 and MPEG 2 compress video by examining both redundancy within a single frame, spatial, and redundancy between frames, temporal. By using the limits of human vision, they further reduce the bitrate. A color picture can be represented by separate red, green, and blue signals, RGB, but MPEG begins by converting these into YCR-CB components, Y for brightness, and CR and CB for color differences. A still frame can be described either as pixel values or as two-dimensional frequency coefficients. MPEG reduces this data by quantizing these coefficients and trimming low-energy ones to 0. Quantizer matrices help choose perceptual weightings so that the steps match what viewers notice. In most images, high-frequency detail is limited, so many coefficients become 0. MPEG then reshapes the two-dimensional block into a one-dimensional sequence and applies variable length coding VLC. These sequences are compressed further using Huffman coding, giving the shortest codes to the most common values. The process described so far treats the picture like a still image, similar to JPEG, assuming nothing changes over time. But video does change, and even more reduction is possible by predicting new pictures from earlier or later ones. Most MPEG savings come from using temporal redundancy between frames. Since video frames are closely related, only the differences need to be coded. This is done through motion-compensated interframe coding, which uses similarities from both past and future frames to reduce bitrate. In this method, macro blocks in the new frame are compared to blocks in previous frames. Any part of the image that does not match becomes the residual error that must be coded. MPEG uses three types of frames to balance reliable reference points with compression efficiency. To decode video, the MPEG decoder reverses these steps. It retrieves the bits from the buffer, unpacks them, and decodes the run-length sequences. Motion vectors and coefficients are stored until needed for the next picture. Data is placed into 8 by 8 blocks of quantized DCT coefficients and then dequantized using step size information. The inverse DCT converts this into pixels or prediction errors. A predicted picture is created using motion vectors to shift macro blocks from the previous decoded frame. Finally, the pixel data is added to this predicted frame to produce the full new picture. The MPEG-1 video standard defines a compression method designed for low bit rates of around 1.4 megabits per second. It works as a frame-based system that uses a fixed data rate. One main purpose of MPEG-1 is to reduce audio and video bit rates so they fit within the 1.41 megabits per second transfer speed of a compact disc, making it possible to store about 72 minutes of video on a CD and play it back in real time. MPEG-1 also supports sending video over computer networks and other similar uses. The MPEG-2 video standard is designed for higher bit rates than MPEG-1. It also uses a variable data rate, which improves coding efficiency and allows better picture quality. MPEG-2 provides a set of data reduction tools and defines 5 profiles and 4 levels. A profile describes how the bit stream is created, while a level sets limits such as picture size, resolution, and bit rate. MPEG-2 is a superset of MPEG-1, so any MPEG-2 decoder can also read an MPEG-1 bit stream. It supports both interlaced and progressive scan video. The standard defines the compression syntax, but the actual encoder design is up to manufacturers, so picture quality depends on the specific implementation. MPEG-2 compression is used in direct satellite broadcasting, DBS, in DVD video and Blu-ray discs, and in DTV broadcasting, each at different quality settings. Although MPEG-1 and MPEG-2 include audio compression methods, other formats, such as Dolby Digital, can be used for audio instead. If you've learned anything new so far, please like the video. It really helps the channel grow. Thank you. The Advanced Television Systems Committee, ATSC, standard defines how digital TV signals are sent and received, but it does not specify just one format. Because development took many years, because the TV and computer industries had different goals, and because flexibility was important, the result was an umbrella system that supports many picture resolutions and features. As a result, DTV can appear as SDTV, Standard Definition Television, or HDTV, High Definition Television, each with multiple protocols. Picture quality in these systems is far better than in any analog consumer format. The reason for supporting both HD and SD formats is the economics of bandwidth. HDTV needs much more data, so one HDTV channel uses the entire broadcast bandwidth. Beyond offering better images, widescreen displays, and surround sound, a DTV signal is also more dependable and less noisy than analog TV. Picture quality stays consistent across the coverage area. However, once you move outside that area, reception does not fade slowly. It is either acceptable or it fails completely. Within the SDTV and HDTV categories, the ATSC standard defines several formats. HDTV provides higher resolution than SDTV, shown by the greater number of horizontal and vertical pixels in the picture. The formats also differ by progressive, P, or interlaced, I, scanning. Traditional TV uses interlaced scanning, showing odd-numbered lines first, and then even-numbered lines to form one frame 30 times per second, originally to avoid flicker. Computer screens, however, use progressive scanning, which draws all lines in order. The ATSC DTV standard outlines how video, audio, data, and broadcast signals are transmitted. In broad terms, the system includes 3 parts: source coding and compression, service multiplexing and transport, and RF transmission. Source coding covers methods for reducing bit rate. Video compression is based on MPEG-2, and audio compression uses Dolby Digital AC3. The DTV standard sets audio bit rates at 384 kilobits per second for the main audio service, 192 kilobits per second for two-channel dialogue, and 128 kilobits per second for a single-channel service. The main audio service can include 1 to 5.1 channels, and multiple languages can be offered by providing additional main services. Although MPEG-2 and Dolby Digital are key to DTV coding, they are only two parts of a much larger system. The DTV standard also defines how bits are formatted and how the digital signal is broadcast wirelessly or sent through cable. A television must receive the DTV signal, tune it, convert the baseband signal from analog to digital, undo interleaving, correct errors, decode MPEG-2, Dolby Digital, and other data, and then turn that information into a high-resolution picture and sound. Only well-designed displays can fully show the quality that the DTV signal contains. Commercial broadcast networks have adopted digital TV in various ways. DTV receivers are built to handle all DTV formats, meaning they can accept signals such as 1080i or 720p and process them. However, even if a device receives an HDTV signal, it might not show it in full HD. Some models convert the incoming HD signal into a lower quality SDTV picture instead. Several security features and protection tools have also been created for use with DTV systems. Thank you for watching till the end. To better understand each video, make sure to watch the previous ones. Some may serve as prerequisites for the next. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.